All right, I think we are ready to get going here. So today, like I said, we're going to focus on exponential functions. And my first question for you is, what is it to be exponential? What does that mean? Okay, so that's a good way of looking at it. The further you go, if you're talking on the x scale, the more quickly it's going to increase. Okay, so it's a what we call it's an increasing function at an increasing rate. It increases at an increasing rate. Okay, another way to kind of look at that idea is that an exponential function is it's multiplication that gets repeated over and over again. So, like for example, let's just look at a little bit of data here that is exponential in nature. I'm going to show you what I'm talking about. Okay, so if I have my x's just go 1, 2, 3, 4, 5. Let's say my y over here is at 6. Then it's 12. Then it's 24. Then it's 48. Then it's 96, etc. You guys all catch the pattern I had going there? Okay. What's my pattern? It's doubling each time. Okay. So while up top, from one number to the next, I'm just going up plus 1, plus 1, plus 1. I'm just adding 1 each time. The pattern in my y's is a repeated multiplication. Each time I go from one to the next, I'm multiplying by 2, multiplying by 2, multiplying by 2. Okay? So that's what's going to create this exponential look to it. If I were to graph that thing, I'm not going to, but because it gets really, really large here. But it would have that exponential heading up really, really quick kind of a look to it. Okay? So if I was going to make an equation for this, or turn it into a function, okay, the exponentials are always going to be of the form a times b to the x. All right, because this little x up here, that exponent, that represents how many times you're multiplying. Okay, and b we call the base. So that's the number that you're multiplying with each time. Okay? So in this case, what's my base? 2, right? That's the number I'm multiplying over and over and over and over again. So for this one, we've got f of x equals a times 2 to the x. Okay? Then the question just becomes, what's the a? And the a we call our initial value. That's where we began. Okay? So what do you think a should be? Okay? In this case, it looks like it should be 6. It's not actually 6, though. Think about this. When you plug in a 1, what are you supposed to get out for y? Based on my data that I gave you there. Should get a 6. Okay? If this is a 6, if a were 6 and I plugged in a 1, what would I get? If a were 6 and x were 1, what would I get?
36.
No. 12. Okay? So, I'm kind of 1 removed, right? From where I should be. So, kind of take the pattern back 1 more. What should a actually be? 3. Okay? Try that now. If I have a is 3, okay, now try plugging some numbers in. If I plug in a 1, I get 3 times 2 to the first. What's that? 6. If I plug in a 2, 3 times 2 squared. which is 3 times 4, 12. It works, right? You can keep doing that. Okay? So this would be an equation that models this situation. Okay? So in general, here are some things you need to remember about piecing one of these together. The b, she said, is the base. That is the number that is getting multiplied over and over again. So the number that is repeatedly multiplied. There we go. Okay. And then the a is your initial value. Which we just need to remember is when x equals 0, not when x equals 1. Okay? So we're going to look at doing some, modeling some situations using exponential equations. And we're going to have to keep these two things straight to help us do it. Okay? So I said I was going to get to that last, but I think I'll actually go there right now because that kind of relates to what we're talking about here. So I'll give you a situation. Let's see if we can pick out what's the initial value, what's the base, and then piece together an exponential equation that'll work for that. So let's say we got a mouse population. So it begins with 20 mice. Probably shouldn't do every day. That's not realistic. Let's say how about every month? Sorry. I just want to make this thing at least seem a little realistic. So every month, let's say the population triples. So write an equation to model the population. And determine how many mice there were after a year. Okay, so this is somewhat realistic. I don't know, tripling every month, it's maybe a little high still, but a little better than every day. So we can pull out some information from this, like I said, to help build this equation, or this function, and then use that function to help us. The part that we ultimately want to know is how many are there after a year. Okay. Now, there is a way to kind of manually do this one as well, which we'll talk about. It's a valid way of doing it. But I want to focus on the function part of it too, because that's important. So, for this one, what would be our initial value of our mice population? 20. And what's our base? What are we continually multiplying that 20 by? 3, right? It triples, so we have to multiply by 3, multiply by 3. Every month we would multiply by 3 again, right? So B is 3. So this mouse population, so I'm going to use M for mice and T for time, okay? Just to get you used to using some other variables here. So M of T equals 20 times 3 to the T. Okay, so then what would I need to do with that equation to answer the question to figure out how many mice there were after a year? You'd put 12 in for T. Yep. Because T is time measured in months, right? Because that's the way I gave you the information, so you have to use it that way. So M of 12 equals 20 times 3 to the 12. It's going to be huge. What do we have? Anybody got an answer yet?
Like over a billion.
720. Just 720? It would be a lot more than 720.
I got 10,628,800. That's what I got.
Okay. So say it again. 10 million.
628,820.
Okay. So I don't know what's in the water with those mice, but stay away. There's going to be lots of them. All right. So about 10 million mice. Okay. Some other exponential type equations. So, like with populations tend to grow, so we have exponential growth. We also have exponential decay. If you guys ever worked in, or anybody taken like AP Chem, or just regular chemistry, I think we probably all had at this point, right? You guys talk about half-lives in chemistry? Yeah. Okay, certain elements have a half-life of a certain amount of time. Okay, so let's try something with that and use kind of the same idea. So I'm going to make up an element. Let's call it benjamonium. Has a half-life of 45 minutes. Okay, so let's stop there and make sure we understand that concept real quick. What does that mean? A half-life of 45 minutes. Every 45 minutes, there's half as much as there was, okay, when it started. So if I started with 10 grams of benjamonium, after 45 minutes, I'd have 5 grams. And then after another 45 minutes, I'd have 2.5 grams, and et cetera, et cetera. So, okay, that's what that means. So let's say our lab contains 200 grams of benjamonium. So let's try and figure out how much is left after 400 minutes. Okay. So some of you guys are probably looking at this thing and saying, okay, I got them. I know how to do this without doing an equation. Every time 45 minutes goes past, I can just take that number and divide it by 2. And I should be able to do this without making an equation, and that'll be easy. Okay? But what's the problem here? Why can't you do that? You'd have to do it a lot of times, but not only that, does 45 go into 400? It doesn't go in evenly. So we wouldn't have a nice, neat number of times. We could probably get close, but we wouldn't know right on. Okay? Now, this mouse one we just did, that one you can, right? What could you do to kind of manually work your way through that without having to use an equation? Just think about the situation logically. You've got 20 mice. Every month, this population triples. You know you got to do it 12 months. Right. So you take your calculator and say, okay, 20 times 3. Enter. 1 time. Times 3. Enter. 2 months. Times 3. Times 3. Times 3. Can you just keep doing times 3 until you've done it 12 times and done? Right? You don't need an equation to do that. Okay? This particular one, yeah, we do. So, Now this one's a little bit trickier